Pleasure to welcome Maxime Bergeron from University of Chicago. He's going to be telling us about the topology of representation varieties.
Well, thanks for having me here and not warning me about the video till the last minute. So it's my first time, so I get to watch myself later, and I'm all over that. So I want to tell you guys a bit about the topology of representation varieties. And so I guess I'm not going to assume anybody knows too much about it, even though maybe since it's the gear seminar I should. So I need two ingredients to kind of tell you about these objects. The first is a finitely generated group, of which I'm going to be kind of studying the representation theory. And the second is kind of a target into which I'm going to be looking at representations. And so initially, maybe I'm going to say this is a Lie group, although later we're going to specialize this to kind of more restrictive classes. And then if I want to tell you about a topology on this space of homomorphisms from gamma to G that I will be studying, these are just homomorphisms that I'm going to usually call rho, from gamma into G. There's kind of fancier ways, but the most down-to-earth way to think about these is to kind of use the generating set and the evaluation map to endow this space with a topology. So what do I mean by that? I mean that I can embed this space here inside the R-fold product of G, so one copy for each generator, and then I can identify this space via the evaluation map, which sends each generator to its value under that homomorphism. So this kind of carves me out a nice little space inside of this space, and since here I have a topology, I can just give this space the subspace topology. So the thing that makes it a little bit nicer sometimes is that if G is algebraic, so for most purposes, you can just think something like SLNC. What we end up getting is actually, through this construction, is a genuine variety which is carved out by the polynomial relations of gamma. So what do I mean by that? Well, gamma is actually, so it's generated by gamma 1 through gamma r, and then there's some relators, and those relators are polynomials, and essentially what you're looking at is R tuples of elements of the group G that satisfies those relators. Since those are all polynomials, I get a genuine variety. So the most kind of concrete example to keep in mind is something like, if you're just looking at commuting tuples, you're just looking at R tuples of matrices in G that commute with each other. So this is an intersection of quadrics inside of the product of the copies of G, say if G is SLNC. So maybe just a quick word about why one might care about these spaces and their topology. So there's this fact that when gamma is the fundamental group of manifold, then this space Hom gamma G of representation, it parametrizes framed flat connections. Whoa. It parametrizes framed flat connections.
So is this a representation variety, or are you going to quotient?
Well, so there's a lot of kind of hocus pocus about what is the character variety, what is the representation variety. For me, this is the representation variety, and whenever I'm taking a quotient, which I will later, I'm going to talk about the character variety. So this is genuinely the space of representations without modding out by any equivalence relation. So that's why the framing is here. So I have to remember the framing, and later we're going to be modding out by a conjugation action, and then this word can be omitted. So framed flat connections on principal G bundles over M. And if you care about this kind of object, then knowing stuff about the topology of Hom gamma G, for instance, its number of connected components, tells you something about the components in this space. So I think that's all I want to say in terms of extrinsic motivation, but intrinsically, I just find that these are very interesting varieties to play with. So from my point of view, they're just intrinsically interesting spaces. Okay, so to get into what I want to talk about more precisely today, so as I mentioned before, G can be something like SLNC, but to be completely precise, for me, G is the complex or the real points of a possibly disconnected reductive, I'll say a word about that in a second, linear algebraic group. So I'll touch a bit on the definition of reductive, but in English what this really means is you take your favorite matrix group, such as SLNC, the symplectic group, I don't know, the general linear groups, and then you just plug in the real or the complex points in there. And the reason why I'm going to restrict to this specific class of groups is because in this case, the variety that you get is going to be very nicely behaved. Okay, so, but to touch upon what it really means to be reductive, so the kind of fancy definition is no, I'll tell you why the fancy is good and bad. So no normal connected unipotent subgroup where here, what do I mean by unipotent? I mean subgroups that kind of are sitting inside of the upper triangular matrices with ones on the lower diagonal. And the reason why we're trying to rule these out is because somehow having normal connected unipotent subgroups of this form will create this phenomena where when you're looking at representations of G itself, you might have invariant subspaces that don't admit an invariant complement. So these kind of matrices tend to suck complements into invariant subspaces, and that's bad behavior that we're trying to rule out. And so since I'm in characteristic 0, so the reason I guess people like this definition is that it generalizes to characteristic P. But in characteristic 0, the best way I think to think about a reductive algebraic group is just it's those groups such that their representation theory behaves like that of finite groups. In other words, every representation is just a direct sum of irreducibles. And that's kind of why people tend to want to restrict to this class in this context. So I'll say all reps of G. So I'm emphasizing the G because I switched from gamma to G on you temporarily. And I'll call that completely reducible. Okay, so this is kind of the second main character. So first, finitely generated group. The second one is a target, such as SLNC. And what we really mean by SLNC is stuff that axiomatically behaves like the properties I've put on the board. And now the goal of all this from my point of view is that I want to use algebraic topology to understand the space Hom gamma G of representations. So my goal is use algebraic topology to understand the space Hom gamma G. So right off the bat, there's a little bit of a problem in that a lot of the techniques of algebraic topology, they work best when you have a compact space. And similarly, if you're thinking about these from a Lie theoretic point of view, whenever your target is a compact group, then you have things like the exponential map is always surjective, and that allows you to kind of use lots of techniques to get at this space. But if G is something like SLNC, none of that really quite works because the space of representations won't be compact. So if you're taking the perspective that you want to understand these spaces through algebraic topology, you immediately run into a problem that Hom gamma G is not compact. And so the first kind of naive iteration to get around this problem is you say, well, Hom gamma G has a kind of natural, in some sense, compact space sitting inside of it. Namely, you can take the subspace Hom gamma K, where K is a maximal subgroup, maximal compact subgroup of G, and look at this space of representations. So those representations that happen to land inside a given maximal compact subgroup. So naively, you can take K inside of G, maximal compact, and try to consider this subspace of compact representations instead. And to give you a flavor is that the moment you start restricting to compact targets, there's a lot of stuff that's known. So maybe I'll say for nice gamma and many k, I'll say much is known. And I'll give you one example about what I mean by stuff can be known in that context. So, for instance, the fundamental group of, so I need to base it, so I'm going to take the connected component of the trivial representation. This is simply isomorphic to the fundamental group of K, and I guess R copies of it. So remembering my convention that gamma is generated by R elements. So this is a result of Gomez, Petit, and Soto. And I'll say this.
Just a second. So R, is R the smallest number? The rank of gamma?
Yeah, the rank.
Smallest
Yes,
number.
yes. Slightly sloppy. But it's just to give you a flavor that sometimes you can get answers that depend kind of on K. And I'll say also that for certain more specific classes, so this is for all compact groups, and for certain more specific classes, there's kind of formulas that count the connected components and that kind of thing. Oh, sorry, I'm completely lying here. Oh, I zoned out. So, I mean for free Abelian tuples. Yes, false. Sorry, my bad. Okay.
I was wondering because that.
Yes, yes. Thank you for catching that. Yeah. No. Not true. Not true. False. Okay. And okay, I'll say there's more results of that type. So now, what's going on from my point of view is that we know stuff about this space, and then you want to know to which extent do answers in the compact case tell you stuff about the non-compact one. So there's kind of this natural question, which is essentially the main topic of my talk, is the inclusion of Hom gamma k into Hom gamma g a homotopy equivalence? Because if you had a homotopy equivalence, then all of these algebraic topology results you would get down here would immediately lift to the full space of representations. Okay, so the immediate answer is that in general it's not at all. So the spaces Hom gamma g and Hom gamma k will have very little to do with each other, and this can happen dramatically in the sense that sometimes you have entire new components of representations that can appear out of thin air. So maybe the most basic example to give in here is that if you take a co-compact lattice in SL2C, then all of a sudden you get these rigidity phenomena that kick in. And this will imply that the component in the space of representations that contains the inclusion of gamma into SL2C is actually disjoint from the space of representations landing in the maximal compact SU2. So the component, let me call this little guy here iota. So the component containing this representation is disjoint from Hom gamma SU2. So maybe just a silly picture. So if this is kind of the whole space Hom gamma SL2C, then inside here you'll have the subspace of those guys landing in SU2. And of course, the component of the trivial representation will contain some stuff here. But out here you'll have iota, and it doesn't intersect that subspace. So in general, you can't say anything at all. But the first kind of result that showed you that not all is lost is there's a theorem of Petit and Soto that tells you that in this context where you're looking at commuting tuples of matrices, there is actually a strong deformation retract from Hom gamma G onto Hom gamma K. So therefore, you do get kind of this naive thing happening. So I'll state it like this. So what's going on here is that if gamma is free abelian, G is reductive. So you can think SLNC, and K is maximal compact. Then there is actually a strong deformation retraction of Hom Z to the R G onto Hom Z to the R K. So the kind of first thing to say about a theorem like this is, why is it not obvious? Because if people know things about Lie groups, or for instance SLNC, you know that there's this polar decomposition. So you always actually have a strong deformation retract from SLNC onto SUN. So there's a retraction from G onto K. And you might say, well, why can't I just use that retraction to induce a retraction at the level of the Hom spaces? And so,
just a second, so
yes.
what happens in the free group case?
Free group it's trivial because you can use this retraction to just move it down.
So it's obvious there.
Yes, so I guess, yes. For a free group, this retraction is obvious because you can literally just use the factor-wise retraction at the level of G's, and you have no relations to preserve, so no problem. And then you might say, well, is there a way to do it while preserving commutativity? And so the answer to that is actually no. There is no retraction from G onto K which preserves commutativity. So this is a real theorem. Maybe I'll state that because it's kind of interesting.
Well, the free group case,
yeah, so for
zeros example.
It's funny because I guess from my point of view and from this point of view, just understanding the topology of these spaces, like the free group case is uninteresting because you're essentially just studying the topology of the algebraic groups. So maybe I'll just make that point here. So you might think how to prove how to do this. And kind of the first thing you might think of is you want to deform G into K. So you have the polar retraction. So maybe just to rephrase that comment. And then we remember that we have this space of representations, Hom gamma G, is sitting inside of G to the R. And then we could just take such a deformation and move it to K to the R. And then what happens to the restriction down here, and hope that that gives us a retraction onto this compact subspace. And kind of there's this result of Juan Soto that says that for n bigger than or equal to 8, no retraction of SLN onto SUN preserves commutativity. So this is impossible to do. There's low dimensional flukes. For instance, you can do it from like SL2 to SU2 and that kind of thing. But in general, this will never work. So I'll say Soto, no such retraction preserves commutativity. And so while you can restrict a deformation from here to here to this subspace, you're going to be leaving the space of representation. So you're kind of breaking the structure of the space you're trying to analyze. So the question is, well, what can you do? And maybe to just give a flavor of their argument, what they end up doing is they use a kind of stratify and concur approach where you can kind of subdivide the space of commuting tuples according to like, well, okay, maybe I'll say it like this. You can stratify representations I'll call it by type. And what do I mean by type here vaguely is that if you're looking at computing 5 tuples of matrices in S, L, and C, you can simultaneously diagonalize them if you temporarily forget that you can't always diagonalize matrices. And then to that you can associate a kind of direct sum decomposition, namely the coarsest one, such that all those guys are diagonal restricted to it. And then you can try and deform this direct sum decomposition to orthogonalize it and eventually get back down to the compact case. And so this is really kind of technical and hard. And what ends up happening is that you stratify by type, and then on each type you can kind of get a little deformation going, but then gluing them back together and ensuring compatibilities is like a logistical nightmare. But that's what they do. So they stratify by type, and then I'll say they use kind of fiber bundle arguments to extend local deformations and then patch everything together. And so at this point I'd like to point out that so this approach is kind of the bookkeeping is difficult is essentially what's going on here. And kind of by pushing this a little bit further, there's a kind of slightly stronger theorem you can prove, which I thought I'd mention since it's a geometry seminar. And so turning this crank as hard as possible, there's a slight upgrade. And this is a theorem of myself and Matsuto. And you can play the same game for iterated amalgamations of free abelians along free abelians. So if you're taking something like so any group you get by starting out by amalgamating free abelians along free abelians, so then you get the same strong deformation retract from the Hom gamma G onto Hom gamma K. And so this class of groups seems kind of random at first, but there's a cute little consequence. So these are going to be right angle ordinate groups that are defined by trees.
Exactly.
So
Formal ones.
yeah, so I guess so that's essentially the consequence. So there's a theorem that classifies those right angled ordinate groups that are fundamental groups of 3 manifolds, and they're precisely going to fall in this class disjoint unions with triangles. And so since you can get whenever you have a free product, you're good. So Q consequence. So if you take gamma to look something like this, so these are the rags defined by trees. And then there's a result of drums, which says that gamma is a rag and the fundamental group of a 3 manifold if and only if its defining graph is a disjoint union of trees and triangles. It's a disjoint union of trees and triangles. And so triangles, those are just free abelian groups of rank 3. Trees look like this, and disjoint union corresponds to free products. So you get a retraction for this entire class of groups from this stuff. Okay. So at this point, I want to kind of change our perspective. So we could think about this result as generalizing Petit Soto in the direction of kind of you start out with commuting tuples, and then you start iterating in kind of the class of groups between the free group and commuting tuples. But moving in a different direction, you can start thinking, well, can I generalize abelian groups then along the ladder of like nilpotent and solvable? And so that's kind of what I want to talk about next. And the nice thing is that when you're approaching the problem from that point of view, you kind of put the algebraic geometry back into this topology of these character varieties, and you can get a lot more mileage a lot more efficiently. So I guess the slogan here is that topological results, results about algebraic varieties should have algebraic proofs. And the main way that I intend to do that is that we want to replace these kind of fiber bundle arguments, stratifying by type, with kind of some ideas from geometric invariant theory. So we want to remember that there's a kind of a conjugation action of the target group on that space, and we want to kind of use the philosophy that this conjugation action is telling us a lot of stuff about the algebraic structure of the representations. So what I want us to remember is that we have an action of G diagonally on the R-fold product of G by simultaneous conjugation. And so since this space is sitting inside of here, there is a conjugation action of G on the representation by conjugating the image. And normally when we talk about representations, even in the finite group case, we're modding out by this equivalence relation. So I'll say diagonal. And so if we go back to the second thing I wrote on the board at the beginning, there was this framing that we were carrying around. So the real object that certain people care more about is not in fact what I call the representation variety, but indeed the character variety after quotienting out by this action. So the first way around that is you want to take something like a naive quotient of Hom gamma G mod G. But then right away you have the problem, which is that this space won't be Hausdorff. And the reason for that is kind of boils down to the idea that if you have a non-compact linear group acting, you might have orbits that aren't closed. So not Hausdorff. There exists not closed orbits. And so the key to this is to use affine GIT instead. So GIT, geometric invariant theory. So I'll say a word about that. So I guess I'm playing the game back and forth. Since I'm mostly going to be interested in the topology, what I'll give you is actually a topological interpretation of what this algebraic construction is. And so topologically, this GIT thing is going to fix our non-Hausdorffness by putting two bars. And essentially what we're going to be doing is this space is now parametrizing the space of closed orbits. And the way this kind of works out is that we can give it the quotient topology. So maybe I'll do it like this. So I have this map which goes from Hom gamma G to this space Hom gamma G double bar G. And what I'm doing is I'm sending rho to the unique closed orbit in its orbit closure. And this is the key place where you're using this reductive adjective that you're carrying around, because in general that orbit won't be unique. But if you have an action of a reductive algebraic group and you're looking in the closure equivalence class, there's always a unique closed orbit representative, and that is precisely what makes this GIT construction work from a topological point of view. So the unique closed orbit in G acting on rho closure. And maybe just I'll put a concrete example. So if we're thinking about the most naive thing going on, 2 by 2 matrices acted on by conjugation, then here's the easiest non-closed orbit. If you have something like 1, 1, 1, 0, and you're acting by conjugation by these diagonal guys, so this is like SL2 acting by conjugation on itself, then you can make this upper right side as small as you want by taking a limit of these guys. And so what that would be saying is that non-diagonal matrices don't have closed orbits because within their closure, there's the corresponding diagonal one. So this would actually get lumped to the orbit of just the identity matrix. So we're kind of taking away all that non-diagonalizable behavior. Okay, and so why does this do what we want? Well, there's this theorem of Luna, which actually tells us that the topological GIT quotient is the universal one in the category of Hausdorff spaces. So this algebraic construction is giving us exactly the minimal construction we need, even if we only want the topological properties to hold. So GIT is universal in a category of Hausdorff spaces. And then what I want to say is that the main result I want to talk about is that now from this perspective, we can prove a stronger theorem. So this is the theorem of myself. And now if gamma is any finitely generated nilpotent group, so once again, G is a complex or real, maybe disconnected or not connected, it doesn't matter, reductive group, K is any maximal compact subgroup of G. So then two things. The first is we get the same deformation as before, namely Hom gamma G will retract onto Hom gamma K. And now we get a bonus result, which is that we get the same statement at the level of character varieties. So one, there's a deformation from Hom gamma G to Hom gamma K. And two, there's also a deformation from Hom gamma G, GIT to G down to Hom gamma K, single bar K. And the reason there's a single bar there is because all orbits of compact Lie groups are closed. So the Hausdorff issue doesn't arise here. Yes?
So is this result of Luna, is this what's sometimes called the Luna slice theorem?
No.
That's a different.
That's a different theorem. The Luna slice essentially tells you that the slices you know from differential geometry, there's an analog in algebraic. I think he proves this using this, probably. Where am I? Whoa. Okay, so now it's arbitrary, finally generated nilpotent. So interesting thing, it doesn't have to be torsion free, essentially anything. And maybe one question that can come up here is, well, in what sense is Hom gamma K mod K a subspace of this other construction? And then if you think about it from the point of view of closed orbits, then it makes sense. So there's a slight kind of crinkle in the rug here. And maybe just a quick word. So in this version of the theorem, reductive is actually necessary. So if you drop reductive and you start looking at unipotent groups, there's actually counterexamples. And yeah. So reductive is necessary for nilpotent. But I guess it's unclear whether if you're looking at unipotent representations of commuting tuples, maybe you still get a retraction. Okay, so now I want to sketch the proof of this. And I want to sketch it in the most concrete instance possible, so I'll do it for free abelian groups because the proof is completely different in this case as well. So we're going to go back to gamma will be just commuting tuples, so you can think z to the 5. G is SLNC. Essentially what this is doing is just taking out all the algebraic geometry, all the technical parts of algebraic groups out of the argument, and then K is just going to be SUN. So what am I really looking at? I'm looking at commuting tuples sitting inside of the R-fold product of SLNC. And then what I want to remember is, well, SLNC, those are just matrices. So I can think about this as not an abstract variety, but a concretely embedded variety inside the vector space of R-fold product of n by n complex matrices. So now my representation variety is a genuine concrete affine variety sitting inside of here. And this is going to be one of the critical things. So it's funny, you kind of add extra structure onto your variety to prove a theorem, and then it turns out it's going to hold for everybody because it won't depend on the embeddings. And so here I also have my SLNC acting diagonally by conjugation on these guys, and therefore these guys. So this is kind of the setup. And now the reason why I'm making such a fuss out of this space is because the next piece of structure I'm going to talk on is that we have a natural Hermitian inner product on this space of matrices. And this natural Hermitian inner product will induce kind of a norm on the representations. And that's going to be kind of the key to the argument. So note, so this is kind of recall from linear algebra 1. So MNC has a Hermitian inner product, which is often called the Frobenius inner product. And what does it do if I give you two matrices A and B? This is going to be the trace of A star B, where A star is conjugate transpose. So what do I like about this Hermitian inner product? The main feature that I care about is that it's unitary invariant. So the norm is unchanged by conjugation by elements of the compact subgroup. So, which is unitary invariant. Whoa. And so what's going to start happening is that we're going to have norms on the representations, and we're going to use this conjugation action to start minimizing the norms. So it's kind of like an algebraic version of a Morse theory argument. And the key feature is going to be that normal matrices are the critical points of this norm on the space of matrices. And then normal matrices are just close enough to being unitary that we can do the trick. So another recall from linear algebra, if you have a matrix in MNC, it's called normal. Here are some different conditions. The first is it commutes with its adjoint. And the second, which is the one that gives the flavor of what's going on, is that M has an orthogonal eigenvector basis. So those are the ones that are orthogonally diagonalizable matrices. So M has orthogonal eigenbasis. So this is the thing that tells us that this is kind of touching base a little bit with that early version of Petit and Soto, where they're trying to kind of orthogonalize the various simultaneous eigenspaces of the representations. And then the third one, which touches with this inner product, is that the norm of any matrix, so here I'm measuring the norm in that inner product over there, so it's equal to the sum of the modulus squared of its eigenvalues. And the key fact is that in general, this is always bounded from below by that, and you're normal if and only if you get equality in this statement over here. So the normal matrices are the critical points of this norm function on the space of matrices. Okay. So what this is telling us is essentially that analyzing the variation of the norms of the matrices is not an entirely futile exercise to do in this case. And the nice thing is that this is precisely the kind of setup that a lot of algebraic geometry is developed to deal with. So there's nice tools for this, and those tools are called, depends who's talking about them, but whoop, it's essentially called Kem Finesse Theory. So Kem Finesse Theory is kind of this hybrid between complex algebraic geometry and complex topology, where if you have any algebraic group, reductive algebraic group sitting inside some GLV, which is acting on some vector space which contains a nice variety to which this action restricts nicely. So I'll say, so here V is a C vector space with a K invariant norm. X is a subvariety. So here, K, as usual, is a maximal compact subgroup of G. So this is kind of the general setup of this. And then it tells you things about closed orbits. So the theorem of Kem Finesse, it says the following. It says that if you define a functional going from G to the reals, so X is any point on my variety X, and the function is the following, I send the group element to the norm of G acting on that element. So this is going to be essentially my Morse function. So it says two main things. You have a critical point if and only if the orbit is closed. So this functional is going to detect which orbits are closed. So pi x has a critical point if and only if g dot x equals g dot x. The closure. And the second thing is that all critical points are minima. So these functions are convex. And so initially this was just used to kind of construct a compact model for GIT quotients, but then you can kind of also use this to stoop it up to this thing called the Schwartz Theorem. Which says the following, that there exists a strong deformation retraction from X onto this set M, where M is the set of minimal vectors. So you can use kind of the flow induced, roughly this induces a flow, and then they turn the crank of functional analysis to show that things converge, everything behaves well. And so whenever you're in this setup, you always have a retract onto the set of minimal vectors. So M here is the X in X, such that conjugating by anything increases the norm. And I'm calling them vectors. It's not completely false. It's because this always only applies for concretely embedded varieties in a vector space. So the points of my varieties are vector spaces. So now this gives us a strategy going as following. So we have our space of commuting tuples. And we know that it's embedded in some vector space precisely in this kind of scenario. And so we know that there's a retraction onto this mysterious M. And then our goal might be, well, can we find a way to retract this mysterious M onto the target we care about, which is the compact matrices. And so the technical heart of the initial theorem I proved to you, I wrote on the board, is essentially characterizing this set. And the answer is that M is going to consist of those representations whose image consists of normal matrices. So the theorem is that M is equal to those representations rho of gamma is inside normal matrices.
X is the character variety.
No, I haven't quotiented by anything yet.
What is X here?
X is the rep variety.
Oh, X is just...
X is just Hom gamma G.
Oh, okay.
So X is Hom gamma G. And so this theorem tells me I have a retract onto those minimal vector, the representations of minimal norm for my Frobenius inner product. And then this theorem is that those representations are in fact those representations who have image in the normal matrices, which is kind of a weird condition to have on representations. And maybe just a quick comment is that this is false for solvable. So this is why So you can prove that with all this setup, this is not true for solvable representations. And so then the proof is essentially completed by this observation that once your image consists of normal matrices, a matrix is unitary if and only if it's normal and its eigenvalues have unit modulus. And so there's this operation of scaling eigenvalues that allows you to move from this set onto the set Hom gamma k. And then maybe I should add that there's kind of how do you get the second part, which is for the character variety, and then there's kind of this idea that you can. So Kem Finesse theory was initially created to touch base with symplectic geometry, and so it allows you to realize all these things as a symplectic quotient, and then the equivariantness that's lurking inside these retraction allows you to descend it down to the character variety. So maybe I just want to close with two kind of questions. The first is what if gamma is solvable? So the key problem there is, well, no good characterization of what this set of minimal vectors ought to be. Although there are some partial results. For instance, I know that this set M always consists of diagonalizable representations. So there's always, if you're looking at representations of a solvable group inside some SLN, there's always a deformation of that variety onto those representations that are diagonalizable. But we don't quite know how to move any further from that. And then the second kind of question, which touches base with the earlier comment about the theorem of drums, is that so we had this result that if a right-angled Artin group is defined by a tree, then we have such a retraction, but somehow this should not be true at all for general right-angled Artin groups. And so the question I've been wondering a lot about is if you have the pentagon right-angled Artin group, can you kind of construct a cohomology class or something of the sort that would show that you have no such retraction? So therefore that the earlier theorem is kind of tight. I think I'll stop here.
So, I mean, did you look at any other kind of groups, you know, like the surface group or anything?
Well, for surface groups, you can't do it, right?
Well,
So I think they have Higgs bundle computations that show that if you're looking at the character variety, they compute a cohomology class, and they show that it's one thing for the compact. Essentially, it's always zero, right? Because I guess I guess for surface groups, there's invariants that are constantly zero when you're looking at compact representations. If you look at, there's a dictionary, I think, between surface group representations and the kind of Higgs bundle world. Right. And on the Higgs bundle side, there's an invariant which is constantly zero for compact representations, but which is not zero for non-compact ones. And so they know that a certain component doesn't have isomorphic.
I see. So over there, you cannot expect a
no.
close.
Right. I think what you're meaning is that the Higgs field vanishes.
Yes, the Higgs field vanishes. But I'm kind of a very. So for surface group, I guess the thing is that these results are very exceptional and not at all the rule. So generically, this is not at all true. And so it's kind of a fluke that it happens. But solvable groups are just fluky enough that they might also happen. And I feel like pentagon rags are just not fluky enough that it should not happen.
I mean, Ilya, if you want a simple example, it's like just take SL2R or PSL2R, right? The one component of this the character variety is type Miller space.
Yes.
That doesn't, every representation in there, that component is discrete and faithful. So in particular, it does not contain any of the representations to the compact subgroup, which is the circle. So there's an example where we can't possibly retract.
Okay, okay. No, all right, I was looking for something like that. Okay, good. All right.
So you mentioned GIT and Kem Finesse, but you managed to get through without mentioning stability.
How did
you do that?
Well, because I'm only talking about closed points. So, okay, affine GIT and projective GIT are two different beasts. And if you're talking about affine GIT quotients, you can kind of sweep stability under the rug. Essentially, for me, it's closed orbits are polystable, if you want the really technical version. But so no stability issues. I mean, this is the only stability issue I have to deal with, and it's. So this is, in some sense, the most naive geometric invariant theory thing you can do.
Okay, thanks again.